Welcome back, students. Today's lecture is last part of the fourth unit, that is non-resonant reactions and resonant reactions. In the syllabus, if you see, there are 8 parts, and today is the last lecture of the fourth part. Okay. So, in today's lecture, I am going to complete the discussion on resonant reaction, and I will be discussing neutron induced non-resonant reactions, as I have said in the previous lecture. Okay. So, let us quickly go through the content of the previous lecture, where I have spent some time on the non-resonant type of nuclear reaction, where sigma is smooth dependent function of energy, okay, smooth dependence function on energy, and resonant reaction, which is contrary to this reaction, sigma varies dramatically at a few energies of projectiles, which we call as resonant energies. So, at those energies of projectiles, the q value and the projectile energy gives rise to excited state like projectile energy, which will become resonant energy when this value, by adding with q value, gives rise to an excited state, which is the characteristic of the nucleus. Okay. And I have written expression for the cross section of a resonant reaction, considering it as a two-step process, and I have also assumed the collision between the projectile and the nucleus, target nucleus, as the collision between the momentum of the projectile and the impact parameter, and then for different values of orbital angular momentum, we have seen the maximum possible cross section for each value of L is nothing but 2L plus 1 into pi lambda bar square, right. And if we include the spin, we can come up with a general representation like statistical factor omega, right. And then for identical particles, I have included one Kronecker symbol. Then by taking the analogy between damped oscillator and resonant reactions, because in both systems the response is maximum at specific incident values, specific input values. Okay. So, by comparing the strength of the oscillator with the product of the partial widths, what is partial width? It represents the probability for each step to occur, fine, and the eigen frequency is compared with the resonant energy, right, and the damped factor F is equivalent to the total partial width of the nuclear reaction, fine. That was famous Witner formula, Witner formula. So, continuing the salient features of this Witner formula and some examples, I would like to spend some time on resonant reactions. Okay. So, in today's lecture, I will be spending some time on resonant reactions and also neutron induced non-resonant reactions. Neutron induced non-resonant reactions. All right. So, let me start with the formula with which I have ended the previous class, that is Witner formula. Okay. So, this is the total partial width, that is formation width plus decay width, general expression, and this is the oscillator strength equivalent quantity, and this is the resonant energy, and this is the Kronecker symbol, and this will reduce to 2L plus 1 if spins are not included, but for general expression we have included both orbital angular momentum and also the spin of the entities in entrance channel. Okay. And this is, as you know very well, quantum mechanically pi r square, that is the geometrical cross section, that is area seen by the projectile. The area seen by the target when projectile falls on it is replaced with pi lambda bar square, right. So, this is the equation which we have derived in the previous lecture. what to do with this? We need some more discussion to answer a question which I have posed in the previous lecture. What kind of resonances play important role? What kind of resonances play important role to decide the properties of the stars? Low energy resonances or high energy resonances? To understand this, we need to take some interesting approach. Okay? It follows like this. See, this Britt-Wigner formula valid for isolated resonances. So, basically when I am saying resonant reactions, it has two properties, that is isolated resonances and narrow resonances. So, when I say isolated means in terms of total partial width, which is the sum of the formation width and decay width. This is greater than the separation between the excited states of compound nucleus. The width of the state which was populated because of the nuclear reaction, the width of the state which was populated by the nuclear reaction should be greater than the separation of the nuclear levels. That is what we mean by isolated resonances. And when I say narrow resonance means the total width, that is sum of the formation and decay width, should be much less than the projectile energy at which this resonance is happening. Okay? That means the total width is constant over total resonance width. What the resonance region is there? Throughout the resonance energy region, total width should be constant. That is what we mean by narrow resonance, isolated and narrow resonance. Alright. Considering this, the stellar reaction rate which we are waiting for to write down based on this cross section formula looks like this. Okay. Before that, let me write down the general expression for the stellar reaction rate. So, this is a well known quantity, energy, center of mass energy, and here the cross section is replaced with Britt-Wigner formula, which depends on the energy slightly, okay, though it is a resonance energy region. Okay. So, we have taken a general representation, that is in sigma as a function of energy, and anyway the particles are distributed according to Maxwell-Boltzmann form. Okay. So, this is a well known reaction rate formula. Now, replace this cross section with the Britt-Wigner formula, this one. Okay. So, for narrow resonance if you consider, then the change in this Maxwell-Boltzmann distribution is very small, because the resonance is happening at a very sharp value of the energy. Around that, if you consider the distribution of the velocities, the change is very small. So, e to the power of minus e by kT will be very small. So, by saying this, I am taking this quantity outside the integral, fine. Then the reaction rate can be represented by this equation, where the energy is also taken out, because we are dealing with a resonant reaction, right, and this energy at ER, I mean this e to the power of minus e by kT at ER is constant, it can be taken outside, and the Britt-Wigner formula is inside this integral. Now, the task is to calculate the value of this integral. So, I will not go into the details, you can do easily using the expression in the very first place which I have written. You need to calculate the value of this integral. So, the final result I am showing. Okay. So, the integral of this Britt-Wigner cross section of the nuclear reaction, resonant reaction given by the Britt-Wigner, it can be derived as like this, alright, where this is the reduced de Broglie wavelength, statistical factor, formation partial width, decay partial width and total width, alright. So, let me use a symbol, this gamma, for the ratio of product of the widths and this total width. So, one more confusing parameter. Already for partial width, whatever symbol we are using, that also is being termed as gamma, and the electromagnetic radiation which is coming out in radiative capture type of reactions, that is also we are using there also we are using the word gamma radiation, and here for the ratio of product of partial widths and the total partial width, here also I am using the symbol gamma. This is not any nuclear radiation, it is not, okay, any gamma nuclear electromagnetic radiation, but this is a symbol which denotes, okay, which denotes basically omega into this gamma, all right. So, this is called as resonance strength, and omega is a statistical factor which involves J, J1, J2, and gamma symbol involves gamma A by gamma A gamma B divided by gamma. So, please remember there is omega here, statistical factor. This is called as the strength of the resonance. Why I am emphasizing this word? Because this is one of the experimentally measurable parameter to understand the cross section of the resonant reactions. Okay? So, resonance strength is represented by the statistical factor and the ratio of product of partial widths corresponding to formation and decay width and the total partial width, that is sum of these partial widths. This gives us information about the strength of the resonance, all right. So, use this for representing the reaction rate in future. Okay. At incident projectile energy equivalent to resonant energy, the cross section exactly at that particular energy I can write down by replacing E as exactly ER, then by taking the help of this integral and remaining things, I can come up with this kind of expression. At exactly resonant energy, the cross section of the resonant nuclear reaction can be represented as 4 pi and de Broglie wavelength at the resonant energy, statistical factor, and gamma A, gamma B and total partial width, that is gamma square, all right. So, this leads to, in terms of this sigma r, I can always write down the integral value like this. So, this is just rewriting the expression of cross section at ER and the integral symbol, there is no much difference. Okay. Now, the area under the resonance curve is given by the total width and the height sigma r. So, the reason for expressing this integral in terms of sigma r is following. Okay. Now, earlier when you have taken the plot of the probability and the energy, and initially when you take this Maxwell-Boltzmann distribution, okay, isn't it, e to the power of minus E by kT, there is a sharp peak at resonant energy. So, this is basically your E into E as a subscript R. So, the gamma peak at which majority of the nuclear reactions used to take place for non-resonant reaction is just replaced with resonance peak. At this particular value, cross section is very high. At this value only majority of the reaction take place, at remaining places no. So, that is how we have initially defined the nuclear reactions when cross section changes suddenly at particular value of energy, all right. So, the area of this resonance curve is nothing but the total partial width and the height is nothing but this cross section R. So, taking this, let me write down the final expression for reaction rate when resonant reactions are discussed. Okay. So, this is the strength of resonance exactly at the resonant energy, and this is the Maxwell-Boltzmann distribution term, and this is the electron screening factor. Though it is negligible, just for the sake of representation, I am including this F also in reaction rate. If at all the stellar density is very high, one has to take into account this electron screening factor. Okay. Fine. So, this is nothing but stellar reaction rate per particle pair, because sigma v is there, and if you multiply with Avogadro number, then no need to write down the per particle pair. Okay. But for narrow resonance, this reaction rate expression is for narrow resonance, not broad resonances, all right. So, to measure the nuclear reaction rate, what one should find out? The strength of the resonance, width of the resonance and the resonance energy. These three are the parameters one has to measure experimentally, so that one can come up with reaction rate directly. You see here in this expression of reaction rate, there is no cross section formula. There is no cross section term involved in this reaction rate for narrow and isolated resonances. Just measure the width of the resonance, just measure the strength of the resonance, and anyway incident projectile energy is known, measure it accurately, you are done with the reaction rate measurement for narrow resonant reactions. Okay? Alright. So, as I said, the gamma peak is replaced with resonance energy ER. The centroid of the gamma peak is nothing but the centroid of the resonance peak, that is the resonance energy ER. Earlier it was E naught. Okay? Gamma peak centroid was E naught. So, the nuclear burning take place at a narrow resonance. Nuclear reactions, the burning happens at these narrow resonances only. Okay? Alright. If more narrow resonances are involved in the reactions, how do you express this cross reaction rate? Simply take the summation of strengths of the resonances. Simply take the summation of strengths of resonances, that will take care of this reaction rate when many narrow resonances are involved. Okay? Now, I am going to discuss one of the very important feature of this nuclear astrophysics, and that is the importance of low energy resonances. Okay? For the sake of simplicity, let us consider this reaction where projectile X is reacting with target nucleus A, giving rise to product nucleus B and gamma ray in two-step process. Remember, if it is one-step process, then it is basically non-resonant reaction. There is no point in discussing this topic. If this radiative capture reaction happens in two steps, formation and decay width term, then in general the decay width, that is gamma decay width, because we are assuming this as a radiative capture reaction, it is very less, sometimes of the order of 1 electron volt or less than 1 electron volt, very less. This very less value of the gamma decay partial width is going to play a very important role. Please pay attention to this topic. I want your special attention to this particular discussion. Okay? So, I am trying to discuss the importance of low energy resonances. For that, I have considered a reaction, okay, where X is reacting with A and giving rise to gamma ray and B, product nucleus. So, there are two partial widths, okay, gamma X and gamma gamma. This is the formation width and this is the decay width. In general, the decay width is always less or equal to 1 electron volt. Alright. Now, I am bringing this statement: if the resonance energy is near the Coulomb barrier, please listen to this carefully. If at all the resonance energy is near to Coulomb barrier, remember, in any case it is happening only above the Q value of the reaction. Okay? But if resonance energy is near the Coulomb barrier, then the formation width is of the order of MeV. So that the omega gamma if you take and statistical factor is considered to be 1, okay, omega is equal to 1, then here this total width is nothing but gamma x plus gamma gamma, alright, and already I have said gamma x is very large. So, this can be neglected and this will get cancelled. Finally, you are left with gamma gamma. The strength of the resonance is decided by the very low value of the decay width, gamma decay width. Fine. If the resonant energy is far below Coulomb barrier, then please ignore this, then this formation width is no more of the order of MeV. It is much less than the decay width. If at all resonant energy is much less than the Coulomb barrier. Remember, many times at very low energies when compared to the Coulomb barrier, actually nuclear reactions are taking place. This you have to keep it in mind. Okay? So, the formation width is much less than the decay width, and because of this, what will happen, my dear? This strength of the resonances here, same gamma x plus, just let me erase the earlier one. Okay? Great. Okay. So, this is the formation width and gamma gamma. Now, here this is much less than this. So, this can be neglected, right, and this will get cancelled. Finally, you have the formation width, which is much less than the decay width value, I mean much less than 1 electron volt. So, what does it mean? The resonance strength decreases very rapidly due to barrier penetration term in formation width. Why? Because formation partial width considers the barrier penetration phenomenon, not the decay width. This you have to understand, okay. And from the reaction rate, we can write down this equation which I have shown in the previous slide. I am continuing with that. From this reaction rate, you can see this term especially. Please pay attention here. This is very important, okay. Resonances with values of energies near kT dominates the reaction rate. See, nowhere you have energy and kT in this expression except here. So, if ER and kT are comparable to each other, then this reaction rate is maximum, okay. So, basically the resonances with ER and near kT only will dominate the reaction rate, So, for low temperatures, see kT, please remember kT. So, at low values of temperature, that means at low values of kT, that means at low values of resonant energies, it is very important to know the locations and the strength of the low energy resonances, not high energy resonances are important. So, I hope you are following what I am trying to convey, fine. For example, let me take a reaction proton with nitrogen 14 giving rise to oxygen 15 emitting gamma ray, a radiative capture induced by proton. Assume 30 megakelvins temperature, T6 is equal to 30. If you see the ratio of reaction rates at low energy resonance, say 10 keV and at 2 MeV, it comes out to be 10 to the power of 312. Please do the calculation, okay. For more details, please look into the textbook, okay, Rolfs and Rodney. Otherwise, we can assume some values and see how it is very important. So, this tells us the mean lifetime of the nuclei and the properties of the star change dramatically for a small difference in the resonant energies, okay. Now, if you consider the resonant reactions induced by neutrons, then the strength of the resonance is nothing but this omega into gamma gamma, which holds for all resonance energies nearly, because in the formation width there is no Coulomb barrier for neutrons. So, it always depends on the partial width of the decay process, second step, okay. Now, the interesting question which I am posing here is nuclei having states with long lifetimes can take part in the reaction. I am talking about the metastable states or sometimes isomers, that means states with longer lifetime. You might have been taught the concept of lasers, there you might be getting the idea of these metastable states where the levels are having longer lifetimes. In stars, when nuclear reactions are happening, sometimes the compound nucleus excited state may possess longer lifetime. So, it will have enough time to react with other nuclei before coming to the ground state. I am talking about this reaction between the other nuclei and the compound nuclei in excited state, not after reaching the ground state, okay. Then how to find such number, okay, Let me take the production rate and the decay rate. So, the production rate is always proportional to number of nuclei in resonant state, that means N1 and N2, okay. And at high resonance energies, if you consider, then the formation width is always greater than decay width, of course not at the low energies, okay. Then this is equal to nothing but total partial width is nothing but which is a sum of formation width and decay width, right, and this is negligible. So, total partial width is nothing but formation width. Accordingly, the strength of the resonance is nothing but decay width will dominate, as I have discussed earlier, because this gamma is nothing but gamma A, gamma B by total gamma, alright my dear. In that case, one can write down the production rate as, this is a well known expression for the production rate. Here I am writing the expression for reaction rate, and there the strength of the resonance is replaced with this gamma B decay width. Now, coming to the decay rate, this decay rate determines the lifetime of the nuclei, right, in the reactions. So, the decay rate is nothing but the ratio of number of nuclei N12 and the lifetime of the N12 nucleus. and using this concept of energy into time is equal to h cross, here partial width, total partial width into time is equal to h cross, I can write down the expression for decay rate. Combining these two terms, decay rate and production rate, I can find out the expression for total number of nuclei presenting in the reaction. This is called as famous Meghnad-Saha equation. So, this is the contribution of Meghnad-Saha in finding out the number of nuclei participating in the reactions within the stars. And the Institute of Nuclear Physics, named after Meghnad-Saha, which is located in Kolkata, Saha Institute of Nuclear Physics, and it is a great coincidence that it is hosting the facility of FRENA, right? Facility for research in experimental nuclear astrophysics, FRENA, right? So, the contribution of Saha we can remember in this particular context. It gives us the number of nuclei participating in the collision, okay? Alright. So, this equation is valid for all reactions when equilibrium is established, because production rate is there and decay rate is there. What is the famous example? In the last lecture, initially I have hinted this point, okay? So, what is the famous example for this number of nuclei participating in the excited state of the compound nucleus? Triple alpha reaction, okay? Alpha plus alpha gives rise to 8 beryllium. This 8 beryllium lifetime is very less. Even then, if the transit time between the alpha particles is small than the lifetime of the beryllium 8, it can again react with the alpha, giving rise to 12 carbon, right. For that, there has to be equilibrium between the production rate of beryllium 8 and decay rate of beryllium 8. Remember, beryllium 8 is highly unstable, okay. So, the ratio of beryllium 8 nuclei and alpha nuclei is found to be 10 to the power of minus 10. It is very small. However, this is sufficient. The ratio of beryllium 8 and alpha particles is not above 1, it is much less, 10 to the power of minus 10. However, it is sufficient to bridge the mass gaps at 5 and 8. How this mass gaps came into picture? In the initial stage of this course, I have discussed one of the fascinating aspect of nuclear astrophysics. I mean, without bridging the gap between at mass numbers 5 and 8, how carbon 12 is formed? Triple alpha reaction. And this is where this formula for nuclei participating in the nuclear reactions comes into picture. So, please remember the contribution of Meghnad-Saha in this particular context, alright. So, in the next lecture, I will discuss neutron induced reactions. Today, because of paucity of time, I could not discuss it. So, let me summarize today's lecture. In the last lecture, I have derived the expression for cross section of a resonant reaction. Taking it forward, earlier I have taken the help of this damped oscillator, and then the importance of low energy resonances. If the resonant energies are near Coulomb barrier or much below the Coulomb barrier, how low energy resonances are playing very important role. The turning point is that the reaction rate corresponding to the low energy and high energy resonances is about 10 to the power of 312, right. So, that is low energy resonances play a very important role in understanding the properties of the stars. And then to know the number of nuclei present when compound nucleus in excited state participates in nuclear reaction with other nucleus, Meghnad-Saha equation really helps us. So, with this, let me complete today's lecture. See you soon. Thank you very much.